we go. And today we have the pleasure to be hosting Dinil Bose. So Dinil is a PhD student at the Observatoire of Côte in Nice, under the supervision of Orla Creevy. And the title of Dinil's thesis is Precise Ages of Stars in the Era of Large Space Missions, Gaia and Plato, and the Link to the Milky Way. So before arriving in France, Dinil did his graduation and post-graduation at Mahatma Gandhi University in India, and he then served as a fellow at the Indian Institute of Space Science and Technology. So Dinil is particularly interested in computer-aided applications, software, as well as in developing tools for astronomy and atmospheric problems. And his areas of interest include open clusters, as we shall see today, asteroseismology, and also high mass star formation. So without any further ado, Dinil, I'll pass the floor to you, and thank you very much for joining us today. Okay. Feel free to share your screen. Are you trying to share your screen, Dinil? Dinil, can you hear us? Just a little mishap. Can you hear us? Dinil, I can see you, and I see that you're typing. Can you? Okay, I guess this connection went down. I see you again. Okay.
Yeah, I'm sorry.
Perfect. No worries about that. Okay. So feel free to share your presentation, and good luck.
Okay, thank you. Okay, can you see my presentation?
We see your web browser, not your presentation yet.
Okay.
There you go.
Yeah.
Okay.
Okay,
good.
sorry about all that. Okay, so thank you, Tiago, for introducing me to the group. Today I will be talking about the cluster NGC 2477 and how I use the asteroseismology to determine the age of the cluster. So today I will start with the outline of my talk. First of all, I will talk about the cluster properties, and then I will talk about the isochrone fitting. Then I will talk about how we found the oscillating stars using the TESS data. Then finally I will use the frequencies from the oscillating stars together with the cluster properties and how I determine the age of the cluster. Okay, so let me introduce NGC 2477. So NGC 2477 is a intermediate age cluster. So when you look into the literature, you can see that the age of the cluster varies from 0.6 to 1.5 gigayears. So now our aim is to precisely determine the age of the cluster. So we study the cluster properties using the Gaia data. Then we do isochrone fitting. So when we do the isochrone fitting, we will be able to determine the mass, luminosity, and temperature for the individual stars. Then we use the mass, luminosity, and temperature to do the asteroseismic modeling. So in order to do the asteroseismic modeling, we need the oscillating stars and the frequencies. So we find the oscillating stars and the frequencies using the TESS full frame images. And we combine it with the properties of the cluster, and we will try to estimate the precise age of the cluster. Okay. So let me introduce the NGC 2477. So on the right, I am showing the TESS full frame image of NGC 2477 observed at sector 7. As you can see, towards the center of the cluster is very dense, and it has a radius of 26 arc minutes. We found the member stars from Canton Gordon catalog. They have used the Gaia data, Gaia distance proper motion in order to estimate the membership probabilities. So we found 2018 member stars. Now I am showing the observed color magnitude diagram of NGC 2477. As you can see, we can clearly see a main sequence stars and red giant stars. So this diagram is not corrected for extinction. So in order to fit the isochrone, we need mainly 3 parameters. First of all, we need distance, metallicity, age, and we also have to correct for extinction. So the distance can be estimated from the Gaia data. So we have precise estimation of distance. So the distance to the cluster is around 1.4 kiloparsec. Now about the metallicity. We have a lot of metallicity observation from various authors. We have metallicity observation from Rave spectroscopy. So Rave has observed around 55 stars. So on the right, I am showing the distribution of metallicity derived from Rave survey. As you can see in the figure, it peaks at minus 0.1 dex. And we also have some high resolution spectroscopy from various authors like Braglia, Cafu, and Maximian. So when we look into the high resolution spectroscopy, on the right, I am showing the metallicity versus temperature diagram for individual stars. The black dots represent the Rave stars, and the high resolution spectroscopy measurements, I have encircled it with a circle. So when we look into the high resolution spectroscopy, we can see that the metallicity varies from 0.06 to 0.16 dex. Okay. Now let's talk about the reddening. Reddening is a measure of dust. So when the light passes through the dust, it gets attenuated. So we have to correct for this attenuation because it's important in calculating the physical parameters like luminosity and temperature. So when we look into the literature, Hartwig and Hesser has done reddening measurements for 26 stars in the cluster, and they found the reddening varies from 0.2 to 0.4 magnitude. So they suggested the cluster may be suffering from differential reddening. We also have Gaia DR2 data, and we also have Gaia extinction measurement for 838 stars, but not for all the stars in the cluster. So we need the measurements for all the stars in the cluster because we are going to do individual models. So we need to correct for individual extinction values. So we took the 3D reddening map by Leleman et al. And we derived the reddening for individual stars. So when we look into the individual reddening of the stars, we found that the reddening is just varying from 0.19 to 0.20 magnitude. And this may be due to
Okay, I think that Dinil might be experiencing some connection problems. Let's just give him a couple of seconds to reconnect. Okay, we have you again, Dinil. Just feel free to continue sharing the screen, okay? There you go. You'll need to unmute yourself. Dinil, you will need to unmute yourself.
Yeah, is it
Okay.
fine? Yeah. Okay. I'm sorry about that again. Don't know what's happening. Okay. So we have the Gaia extinction values for 838 star. So if I plot the Gaia extinction values, you can see that towards the center of the cluster, although Gaia has a large uncertainty, the Gaia is also showing towards the center of the cluster, we have less extinction. Now, if I plot the extinction values from stillism, we can see a gradient which is from bottom left to top right. We can see a gradient, but the stillism has large error, so we cannot use it. So we decided to use the Schlegel et al. Two-dimensional reddening map in order to find the extinction for individual stars. Now, what is the cause of this differential reddening? So we started to look into the dust map. So when we look into the dust map, we look into the dust map from Akari telescope. We have dust map of 90 micron and 140 micron. As you can see, towards the center of the cluster, we see less dust emission. And on the outer regions, we can see more dust emission. So this dust can be in front of the cluster or behind the cluster. So here I am representing the cluster in the center, and I am okay. So the cloud can be in front of the cluster or behind the cluster. And when we look into the Schlegel et al. Reddening map, we are getting a line of sight reddening. So we will get the entire reddening in our line of sight. So now we have to find out the position of this dust cloud. So in order to find out the position of the dust cloud, we again look into the Gaia data. So we took all the stars in the vicinity of the cluster, and then we created different distance bins. For the sake of presentation, I am just introducing two bins. So I took closest stars from 500 to 1000 parsec. Then I took stars from 2000 to 2400 parsec. So these are the farthest stars. So in the figure, I am showing the observed color versus the histogram of the observed color. Now, if you see the top panel, I am plotting all the stars in the region, and you see two peaks. For the closest star, it peaks at 1.25 magnitude, and the farthest star, it peaks at around 1.5 magnitude. Now, I divide the stars into two regions. So I select the stars with extinction less than 0.75 magnitude, and another group with stars with extinction greater than 0.75 magnitude. So if you see the middle panel, if I plot the stars with the extinction less than 0.75 magnitude, you can see both peaks at the same magnitude. And if I plot the stars with greater than 0.75 magnitude, you can see the farthest star have high color. So this indicates that the dust is in between 1000 to 2000 parsec, because when the light from the star passes through this dust, it gets attenuated, and there we can see a shift in the color. So the dust is in front of the cluster or inside the cluster. So this result was supported by Dutra and Biga. They also found that there is a presence of dust, and it may be in front of the cluster or inside the cluster. Now we know the position of the dust. It's let me say it is in front of the cluster. Now we from the Schlegel et al. Map, we have the two-dimensional reddenings. It means that we have the line of sight reddening. So we have to correct for the background reddening in order to find out the extinction of individual stars. Okay. Now we know that the dust is in front of the cluster. So the differential reddening is caused by the dust cloud. So we can safely assume a constant background reddening for the cluster. Now we have to find out the value of background reddening in order to find out the correct extinction for the individual stars. Before I jump into calculation of background reddening, let me talk about some conversions. So in order to convert EB minus V to Gaia extinction, I have used the procedure outlined in Gaia collaboration et al. Paper. Then in order to in order to calculate the temperature, I have used the procedure outlined in Casagrande et al. Paper. And in order to calculate the luminosity, I have used the standard equations. Now we have to estimate the background reddening. So I have used different techniques to estimate the background reddening, but I am only going to talk about one technique here. Okay, so we have rave observations for 55 stars. So the rave spectroscopy gave us temperature for these 55 stars. So now we can calculate the photometric temperature for these stars. Please note that in order to calculate the photometric temperature, we need magnitude, color, and extinction values. So let's take a star S1 as represented here. We first derive the reddening from the Schlegel et al. Map. Then we assume a constant background reddening. Then we subtract this reddening in order to find out the actual reddening. Same for the star 2. We will find out a reddening from Schlegel et al. Map. Then we will assume a constant background reddening and we will subtract it to find out the correct reddening. And now we calculate the photometric temperature using this reddening. Then we compare this photometric temperature with the rave temperature. So here I am showing the chi-square value for different background reddening values. As you can see, the chi-square value decreases, and around 0.34 magnitude, we have less chi-square, indicating that the background reddening value is around 0.34 magnitude. So we did reddening estimation using different techniques, using temperature from rave stars, using temperature from high resolution spectroscopy, using extinction from Gaia DR2, using the properties of red clump stars, and also Dutra and Bika also have calculated the background reddening, and they also have reported it to be 0.36 magnitude. So from all this analysis, we found that the reddening varies from 0.24 to 0.34 magnitude. Okay. Now we know the reddening values. Now we have to correct the reddening for the cluster. So on the left, you can see the observed color magnitude diagram. And on the right, I am showing the color magnitude diagram after the correction of reddening. So as you can see in the figure, if you see the main sequence, after the correction, there is less spread for the main sequence and the red giant star. Okay. Now we have corrected the background reddening. Now we can do isochrone fitting. So in order to do isochrone fitting, I have used 3 isochrones: Parsec, Basti, and Mist. So on the left, I have shown the fitted isochrones. And as you can see, for different isochrones, we have different ages and different metallicity. So here I have used age and metallicity as a free parameter. So on the right, I am showing the distribution of age metallicity as a function of background reddening. So you can see that when I change the background reddening, I am getting different age and metallicity. So from this analysis, we found that the age of the cluster is varying between 0.6 to 1.1 gigayear. So first of all, we did study the properties of the cluster, and after the isochrone fitting, we know that the age is between 0.6 to 1.2 gigayear. Now we have to find oscillating stars in the cluster. In order to find out the oscillating stars in the cluster, we started to look into the TESS data. So here we are using the TESS full frame images because it covers 85% of the sky. And for a sector, it observes around 27 days. And the cadence of TESS full frame images is 30 minutes. Since it's a all sky survey, the pixel size of the TESS is very large. So we have to be very careful with the aperture selection because since we are looking at the stars in the cluster, uh, towards the center of the cluster, we can see that there are close by stars. So if we don't do the proper aperture selection, the light from the nearby stars can contaminate our star. So let me show an example. So this is a target pixel file of one of the stars in our cluster. So I have drawn two apertures. So you can see this, the cross represent the target star. I have drawn two apertures, one is in blue and one is in red. So you can see that the two apertures are giving the same light curve. So this indicates that from the nearby star, this the target star is contaminated. So we cannot use this star for our analysis. So since we have to look into a lot of stars, we developed a graphical user interface for this package. So now I am showing the graphical, a small demonstration of the graphical user interface. Okay. So this is the graphical user interface we have developed. We named the package as TESS iPad. So with this package, we have combined almost all available packages like Lightcurve, Eleanor. So we combined them all and we created this package. So with this package, you can draw custom apertures interactively and you can get the Lightcurve. And we also have added some tools for folding the Lightcurve and creating periodogram, etc. Another feature of this software is that we also combined it with DS9 so that we will be able to see the other stars in the cluster. So here I am showing the DS9. With this, you can see the nearby stars and you can see how it contaminates the target star. Okay. So this package is currently available in GitHub. So you can download the package and you can use it. And please let me know if you find some bugs. So it's still under development. So I will correct the bugs. Now using the software, we found oscillating stars in the cluster. So we found around 26 oscillating stars and 5 candidate binaries. So on the figure on the right, I am showing the oscillating stars. As you can see in the figure, the red represent the oscillating stars and the blue represent the candidate binary stars. We have also found many oscillating stars, but they are contaminated. Now I am showing the examples of oscillating stars which we found in the cluster. So this is an example of an oscillating star. So I am showing the light curve of the oscillating star. As you can see, I have combined the light curve of two sectors and yeah, so it is 54 days long. And on the bottom, I am showing the Lomskargel periodogram. And as you can see, a lot of frequencies are excited. Okay. So this is also another example of an oscillating star. Okay. Now here I am showing the periodogram of a lot of oscillating stars in the cluster. I am showing around 15 oscillating stars. As you can see, there are different type of oscillating stars in the cluster. Now here in this diagram, I am showing a candidate binary star, which is we found from the cluster. Okay. Now with the TESS IPAC package, we found around 26 oscillating stars. Now we did some signal simulation to extract the frequencies. Now we can use these frequencies for astroseismic modeling together with the properties of the stars using the isochrone fitting. Now coming to astroseismic modeling. For astroseismic modeling, we first created the isochrones using Mesa. So we used the default physics as input. Then we created the pulsation modeling models using Gyre. So For constructing of isochrone, we know the parameter space. We found the parameter space by fitting the isochrones. So we know that the metallicity, we took three metallicities, which is 0.06, 0.1, and 0.16 dex. And we have three background extinction values from 0.24 to 0.34 magnitude. And we took the age from 0.6 to 1.1 gigayear. So on the right, I am showing two isochrones, which I took from Bose isochrones. Here I am plotting, we have the metallicity is equal to 0.06 dex and the background extinction 0.34 magnitude. Here I represent each star with luminosity and temperature error. So I will talk about this luminosity and temperature error in the next slide. Okay. So here, if you see 1 gigayear isochrone, which is represented in blue, you can see that it fits the cluster very well. And if you see the red isochrone, which has 0.6 gigayear age, it does not fit the cluster. So we can remove this isochrone from our analysis. So here in this table, I am showing the isochrones which I have used for our analysis. Okay. Now, for creation of isochrone, we need the helium abundance and metallicity value. So we took the we took the same helium abundance as the Bose isochrone. So here I have given the helium abundance and the metallicity values. On the right, you can see I have compared the Mesa isochrone with the Bose isochrone. It is almost similar, but you can see near the turnoff and near the red giant regions, the isochrones are not that similar. This may be due to the difference in physics. Okay. Now, after the creation of isochrone, we can find out the mass of the star. So here I am showing one of the stars, which is represented as cross. This is N77342. So here I have plotted the luminosity temperature error as gray. So we computed the luminosity temperature error because there are a lot of observational errors and there are also extinction errors. So we did a Monte Carlo simulation of luminosity and temperature, and we found out the luminosity temperature error. So here on this zoom diagram, I am showing the density plot of luminosity and temperature. So we try to find out the mass of the stars within the luminosity and temperature error. So as you can see in the figure, from the isochrone, I can estimate the mass of the star. So the mass of the star is from 1.8 solar mass to 1.915 solar mass. So if I know the mass of the star and if I know the chemical composition, I can now compute the pulsation models. So here in this diagram, I am showing the pulsation models. So on the top, I am showing the pulsation models for 1.8 solar mass, and on the bottom, I am showing the pulsation models for 1.9 solar mass. The gray color represent the observed frequencies. As you can see, there are a lot of we have a lot of excited frequencies, and the vertical line shows the theoretical frequencies. Okay. So the L is equal to 0 mode is represented as a black line, and L is equal to 1 mode is represented as a blue line. And L is equal to 2 mode is represented as red line. So let's focus on L is equal to 0 mode. So now I represent the L is equal to 0 mode with the black arrows. As you can see from when we change mass by a bit, we get more frequencies, and the frequencies are shifted towards the left. So even the small change in mass in luminosity and temperature makes a huge difference in frequencies. Okay. Now we computed a lot of models for each and every star. Now we are trying to estimate whether we can find large frequency separation for this star using the pulsation models. So here I am showing pulsation models for different ages. So the top panel, you see the age of the star is 0.8 gigayear, and in the middle panel, the age is 0.9 gigayear, and in the bottom panel, the age is 1.1 gigayear. Now again, let's focus on L is equal to 0 modes. which I will represent it as black arrows. Now you can see these are the L is equal to 0 modes for different ages. Now we are trying to see whether there is large frequency separation. So these are the large frequency separations for the L is equal to 0 mode. Now you can see in the observed diagram, you can see there are three main peaks. So we are trying to see whether these peaks are corresponds to large frequency separation. So when we look into the pulsation models and the observed models, we can see that these peaks corresponds to large frequency separation. So these are the large frequency separation we identified. Now we found a large frequency separation for two stars. One is N77-342. It has a large frequency separation of 30 microhertz, and N77-240, which has a large frequency separation of 36 microhertz. So on the diagram on the right, again, I am showing the HR diagram. Here I have plotted the position of the stars along with the luminosity temperature error. So you can see two stars. Now the aim is to find out an isochrone which fits the large frequency separation of both stars. So in order to do that, in this diagram, I am showing the large frequency separation as a function of mass. So let's focus on the top diagram. Here I have on the first panel, I have represented age as 0.9 gigayear, and on the middle panel, I have represented age as 1 gigayear, and on the last panel, the age is 1.1 gigayear. So here the black dot represent the theoretical large frequency separation for a combination of age, metallicity, and the ellipses represent the observed large frequency separation for N77-240 and N77-342. And the color in the ellipses represent the extinction values. So the aim is to find out a model which fits the large frequency separation of both stars. So as you can see on in the first figure on the left, we cannot find out a model which fits the large frequency separation of both stars. But if you see the age 1.0 gigayear, we can see that this fits the large frequency separation for both stars. This is same for 1.1 gigayear also. So now we look into the individual frequencies. So if you took the model age 1 gigayear and 1.1 gigayear and see the individual frequencies, you can see these are the individual frequencies. When we compare it with the observed frequencies, we can see that the individual frequencies also matches for N77-342. And if you look at the N77-240, you can also again see that the individual frequencies matches with the observed frequencies. Okay, so in conclusion, from the literature, we found the age of the cluster from 0.6 to 1.5 gigayear. And using the properties of the cluster, we did the isochrone fitting, and we found the age varies from 0.6 to 1.2 gigayear. So, and by finding the oscillating stars and doing the asteroseismology, we found that the age is 1 gigayear with a precision of 0.1 gigayear. Okay. So in conclusion, we first developed a package to analyze the TESS full frame images. Then we did a thorough investigation of NGC 2477. We identified variable stars, including binaries. And then we did the analysis on background reddening. Then we did modeling of these stars, and we found the age of the cluster to be between 1 gigayear and 1.1 gigayear. So with the asteroseismology, I can say that we were able to precisely estimate the age of the stars. So thank you for listening to my talk, and I would be happy to answer all your questions.
Okay, so thank you very much, Dinil, for a very interesting talk. So as usual, I will ask those that want to pose questions to please use the raise hand functionality, okay? So before I see any raised hands, let me just break the ice, okay, Dinil? So a very sensitive step in your analysis would be the light curve preparation, right?
Yes.
So are you familiar with a pipeline called PATHOS, which is a PSF-based approach to extracting light curves? And did you compare the performance of that pipeline as compared to yours in reducing the light curves? I would be interested in seeing that.
So in this figure, I have compared the light curve from different packages. You can see PATHOS, Quick Look pipeline by MIT, then our pipeline, TESS FFI. So you can see that this is the light curve for a star, and you can see the power spectra on the bottom. And if you see that we were able to extract a similar frequency compared to PATHOS and QLP. So we compared it, and it's almost similar.
And this would be a cluster, a star belonging to the same cluster.
Yes.
Okay.
So this star is observed both by PATHOS, QLP, and.
Okay. So before I pass it on to others, so where does the cluster membership probability of your stars come from? Did you compute it yourself, or do you take it from the literature? Because that's maybe I missed it, but.
So I took it from Candon-Gowden catalog. So they calculated the membership probabilities using the Gaia data, especially using proper motion and the distance. So I took the members from Candon-Gowden catalog.
Okay, got it. Thank you very much. Okay, so I see a few hands raised. So Vicky, on to you.
Yeah, hi, thanks. Can you hear me?
Yes.
Yes, perfect. Thanks for a nice talk. I have a question and a comment actually concerning the oscillating stars you showed. I couldn't see a frequency value for the Fourier spectrum. Here, so is it, this one here. So what are the frequency values here? Because I can't see them. I guess they're not here.
Okay.
And here, so it's just to get an idea which what time scales we're discussing.
It's up to 273 microhertz.
Okay, so that's about 25 cycles per day. Okay, sorry, I think in cycles per day. But I suppose that these stars are delta Scuti stars, and I would like to issue a little bit of warning here, because delta Scuti stars, first of all, are rapid rotators, can be rapid rotators, and I suppose you did not include rotation in your modeling, did you?
No, we didn't include rotation in the modeling because first of all, we didn't have any observation of rotation towards the cluster. And so that's the reason why we didn't include the rotation in the modeling. But one thing we have to say that the luminosity temperature error, if you see the luminosity temperature error, it's very large. So it's very large. So even if I include the rotation, I think
right. I don't think that will influence your temperature necessarily a lot. It's more in the context of oscillations fitting, because rotation can split the modes, right, and can shift all the frequencies. So this is something, and it's pretty dangerous to just assume that because you have three frequencies that show some sort of a pattern, to assume that these are the large frequency separations. And it does work for several stars, especially when they're young and they have high radial orders excited. But especially for older stars, I would be very cautious to do that. I think I'm old school in that respect, and mode identification becomes really tough. So I think you should take into account rotation and see how the modes are splitting. So that's my comment.
Okay. So
Thank you.
Okay, thank you very much, Vicky. See another hand raised. I presume Handy Moya? Yes.
Good morning. Thank you.
Good morning.
You, for the presentation. Yes, my question was similar to that of Vicky. Was in the sense of there are many things impacting on how delta Scuti models behave, and rotation is one of the main things, but also like overshooting and other things that can change the mass for this chart diagram point, and the position of the frequencies, and also this apparently with your exposition, this I-based identification of new max with delta Scuti stars is a little bit risky. There is one paper of Marguerite Paparot that she do it somehow, but with a more comprehensive study, but not just finding 3 modes apparently X-spaced, and then you claim that you got the delta, the large separation in delta Scuti stars. There are many papers trying to obtain this in the literature, and it's more difficult than that. And only if they are really young, as is in the paper of the embedding, it's more easy because you can see in the shell diagram. But if it's more evolved, it's very difficult. That not with 3. So just it's a warning that because maybe things are more complicated in the delta Scuti framework than in other stars. That's it. But thank you.
Thank you very much, Andy. I see a couple of questions in the chat box. So, but apparently the question by Patricia and Gang Li are quite similar to the comments made by Vicky. Unless, guys, you want to pose the question directly to Dinil, in which case, please feel free. Go ahead, Patricia.
Okay, thank you very much. Good morning to everyone. My question is, I think, probably related to Vicky's, but I would like to ask anyway. I mean, when I saw the slide, Dinil, that you presented with a large frequency separation from the models, you seem to indicate that there is a systematic shift between the model frequency separation and the values of the frequencies themselves. And I was wondering if there was an explanation for that, if you had an explanation for that.
The frequency shift in the models, that's what are you asking?
Yes, well, I do not see that the frequencies that you indicate as fundamental modes, as radial modes, are connected to frequencies that are computed from the observations.
Okay. So
I mean, I see that you can compute the large separation from your model, but I do not see the compatibility between the radial modes themselves and the frequencies that you detected in the observations. Is my question clear to you?
So okay, let me make it clear. So you are saying there is a shift in the theoretical frequency compared to the observed frequency. Is that clear?
Yes, exactly.
So yeah, okay. So here, if you see in this figure, you can see that we have taken the age to be 1 gigayear to 1.1 gigayear. So if I go to a 1.05 gigayear, maybe I will be able to properly fit these frequencies. So even if I change metallicity value by a bit, again the frequencies will shift. So if I want to be more precise, I have to make a more rigid grid so that if I want to fit the observed frequency. So
okay.
Since my grid has a size of 0.1 gigayear and metallicity value is 0.05 dex, that's why we were not able to properly fit the these individual frequencies.
I understand. Yes, I understand your point of view. Thank you very much.
Okay, thank you, Patricia. I see another question in the chat. So a question by Cenk. So how did you isolate the stars from light contamination when you produced the light curves? I think you partially answered that one, but maybe you want to add something else, do you know?
Can you repeat the question once again?
It is in the chat box.
Okay, let me see.
Okay, so how did you isolate the stars from light contamination when you produce the light curves?
Okay. So, yeah. So this is the major problem with when we look at the clusters. So let me say. Okay. First of all, towards the center of the cluster, there are a lot of stars nearby. So there are contamination from the nearby stars. So if I see a contaminated stars, I usually does not use it for my studies because I already have 26 oscillating stars. I would love to get more oscillating stars, but I will not use the contaminated light curve. So I just avoid these stars.
Okay.
So I also look into the Gaia magnitude to see whether there is a foreground star with similar magnitude or brighter magnitude to see whether there is a light which is contaminating the target star. So I also look into Gaia magnitude also to see whether there is light curve contamination.
Okay, thank you. I see Orla has her hand raised. Go ahead, Orla.
Yeah, hi, thanks. I just wanted to just give some brief answer for the questions about the Delta Scuti models. This is true. I entirely agree. We have to be careful with rotation, but in fact, it's the delta nu does not change a whole amount, right? And there's a couple of studies that are available that show a comparison of delta nu rotating and non-rotating cases, and it's in fact the delta nu that we were looking at, right? So I agree, looking at a direct comparison with the frequencies is a much more delicate task. I think this maybe partially answers Vicky's question, or maybe not.
Or maybe not, because Vicky has her hand raised. So go ahead.
Yeah,
Vicky.
just to comment on that, I agree that the delta nu doesn't change with rotation a lot, but what changes are the other frequencies. It's the mode identification that changes and becomes very critical. That's what. So all the other L=1, L=2 modes, and we still have the issue with Delta Scuti stars that not all modes are excited. So we can't actually tell whether one of the components belong to an L=1 or not, whether they're prograde or retrograde modes. Then you have the inclination angle, and so on and so on. And the amplitudes, we don't know what the mechanism behind the triggering the height of the amplitude is. So just careful. I'm not saying it's impossible. It's just be careful. It's dangerous.
Yeah. So, and this is one of the reasons that we use models to help to see if a delta nu could be possible in that region, right? And so, yeah. Okay. Thanks.
Okay, thank you guys. And Dinil, you have a comment from Daniel Rees, so I'll just read it to you. So you might be able to extract light curves from contaminated stars using PCF fitting. So that's actually what the PATHOS pipeline does, right? So you have covered that.
Yeah.
I have a question, because you mentioned at some point in your conclusions that there is a tentative detection of solar-like oscillations in red giants and clump stars, right? But you haven't shown nothing about it. Do you have any slides to share with us?
No, actually. So in this figure, if you see the red giant stars, we have some contaminated oscillating stars, so which are oscillating. So we try to see what are the nu max and the delta nu for these stars. So we found out the nu max. Then when we found out the model, the isochrone, we calculated the theoretical nu max for these stars, and we compared this theoretical nu max with the observed nu max to see whether it is matching. So when we compared this theoretical and the observed nu max for these red giant stars, some of the red giants are actually matching. So this indicates that although the stars are contaminated, still we see oscillations in red giants. So this is what I.
So what sort of nu maxes are we talking about? Very, very low ones, right? We're talking about high luminosity RGB stars.
Yeah, yes. The nu max.
The order of what, 10 microhertz or something like that?
Yeah, yes. That yeah, around that range, 80 to 140 microhertz, that range.
Okay. Antonio, you have your hand raised.
Yes. Yes. Just a quick comment about what they were commenting previously about the changing in the delta nu for delta Scuti stars, what we have found is that the relation between the large separation and the mean density doesn't change, but for sure the large separation changes with rotation, because you change the volume of the star, and others, for example, metallicity can change your mean density. So that's the only point. So you have to take into account the rotational velocity at some point, because if you are fixing your mass in the stars. So that's, I think, that the tighter constraint you have in your modeling. So if you don't fix the max, probably you get better large separation, even when you don't take into account rotation, because you are changing, you are allowing to changing the mean density. That's the thing. Okay.
Thank you very
Thanks.
much, Antonio. Okay, I don't see any hands raised. So if there are no further questions, I think we can finish here. But before we leave, let me announce the next seminar of the series. So it will be the last seminar of the second season. There will be a third season, I presume. And it will be delivered by Alejandro Ramon Balleste on June the 8th, okay? So let me thank Dinil once more. Thank you very much. And let us reconvene in about a month from now, okay? For the last talk of the season. Thank you very much, guys, for attending.
Thank you, Dinil.
Hi, thank you.